Hello, this is Andre Bondi. The subject of my talk is on preventively minimizing the performance impact of black swans. Uh, this talk is inspired by observations about large-scale public-facing websites that appear to have crashed or been slowed down because the nature of the workloads or the nature of possibly changing workloads was not foreseen. And sometimes the social consequences of this lack of foresight have been rather dire, or sometimes they've been a just plain nuisance. In any case, what we see is that we have changing workload patterns that were not expected or not catered for. And these changes can be caused by changing social or political conditions, demand for a scarce or valued commodity such as cheap plane tickets, or nowadays a cheap vaccine. And these are commodities that will only be available for a short amount of time. So there's a massive surge to go in and try and arrange whatever this scarce commodity is that's desired. Another instance is compliance with government deadlines for such things as tax filing, census form completion, or voter registration. The performance consequence is severe degradation or disruption, and usually the disruption occurs either because of a massive increase in load or because of a change in patterns for the invocation of use cases, including increased invocation of particular use cases that cause the system to behave in a performance degrading way. And we'll see more about that as we proceed through the talk. It's worth noting that some usage pattern changes are foreseeable and others not. What I would like to advocate is that before a system is deployed, or even while it's at the design change, models be built that can be used to identify changes in where bottlenecks are going to emerge as the traffic pattern changes. But we also need to identify plausible and extreme workload and testing scenarios that can reveal the problems. And there's a serious management challenge here, and that is persuading management and engineers that testing or modeling the extreme scenarios is necessary to protect services and systems against disruption. And frequently resistance will occur because there's an attitude that it's not likely that the scenario is going to occur, and therefore we don't need to cater for it, and it's probably not going to matter very much anyway. But one of the other challenges that we should meet in avoiding these problems is architecting systems for load scalability and reviewing designs in architecture to prevent the problems from occurring to start with. So my goal, although I won't state it explicitly as we go on, is to advocate the incorporation of steps to prevent these issues in a standard software development lifecycle, whether that's going to be waterfall or agile or anything else. And I would argue that this can be done with well-known existing methods, tools, and processes. Now, I'm going to be talking about a bunch of well-known websites about which I have no direct knowledge whatsoever. I haven't worked with the people who own them. I don't know what their decision processes are. I don't know what their design processes are. I know nothing about their internals. All the analyses and comments that I'm going to make are based solely on press reports and conjectures derived from them based on my own experience. So I have no direct knowledge of the decision or design processes, nor of the discussions by the owners and implementers of these websites. So let's take a look at some examples of overload due to black swans. Some of these have been foreseeable and some of them were not. In 2021, we've seen that COVID registration, vaccine registration websites in the US and Switzerland were saturated with sudden demand when they were opened. The Neue Zürcher Zeitung likened the problem to selling tickets for a rock concert. Apparently, there was concern that there wouldn't be enough vaccines to go around, and that there wouldn't be enough appointments and everybody wanted them. In New Jersey, where I live, and in many other places, the problem was very sudden demand, allocations of priorities, and people being kicked off and scheduling not being done properly. And the result of that is that people retry and retry and retry, and all these retries increase the load on the system horrendously. In 2020, because of the pandemic, we saw a tremendous increase in unemployment claims throughout the United States, and that caused severe overflows on the benefit claims websites. And that load was not foreseen when these websites were built, and in some cases, the websites were somewhat old by modern standards, and they were known to be vulnerable to overload many years for many years after being built. And we'll see more a little bit about that later. In 2019, a bizarre usage pattern emerged on the UK Parliament's grievance petition website. This was not anticipated. What happened there was that there were a large number of signatories trying to stop Brexit by signing a petition, and then many of them would immediately try to get a map showing the geographic distribution of the signatories constituency by constituency. And there was tremendous social interest in that. That was an unforeseen load that slowed things down enormously and made the website unusable. In 2016, there was another Brexit black swan. The voter registration website crashed on the last day to register. That's something that should have been foreseen when built because the size of the voting population is known. We had a similar phenomenon in 2016. In Australia, if I remember rightly, the census website crashed on the form filing date, and the entire country was required to fill in the census form online on that date. And it went down on overload. You find similar phenomena with tax filing software websites and so on as well. There can be tremendous overloads, and I would suggest that this is a problem in any developed country or any country that has online filing. One thing that was not foreseen and in all fairness could not be anticipated was that when President Trump was elected, the Canadian immigration website was saturated by queries from the United States. And in 2001, CNN.com crashed during and right after the 9/11 attack. That was unanticipated. It was unforeseen. The problem there, to which I can attest because I lived through it, was that the phone system broke down, and also the radio station transmission from the World Trade Center was disrupted for the simple reason that the antennas were on top and the thing came down. So it was very difficult to get timely information about what was happening unless the radio stations were broadcasting from the Empire State Building, which was not attacked. Okay. I'm going to focus on two websites, the UK Parliamentary Grievance Petition website and the New Jersey Unemployment Benefits website. And again, I must say that my comments are based entirely on press reports and conjecture. I know nothing about the internals of these things. Okay, so let's look at the UK Parliamentary Grievance Petition website first. The use cases are signing a petition, which means that you have to fill in your name, your address, from which is inferred the constituency in which you live, I suppose, and whether you are actually eligible to sign because you're a British citizen or not. And the other use case to which everybody had access was generating a map showing the numbers of signers in each constituency or region. And anybody could invoke the map generation use case. And they did. And they did. You can imagine that as the number of signatories grew into the millions within a very short amount of time, there was intense interest in up-to-the-minute regional distribution of signatories. And that caused heavy and frequent demand for new maps and slowed the whole thing down. So So it was the map generation that caused the resource overload. And the volume of incoming signatures on its own did not cause the website to slow down. It catered for that. So one might conjecture that it was originally believed that this website would not harbor many petitions that would generate a lot of interest in maps. Of course, Brexit was a very special case. I don't know how this worked, but I conjecture that in an extreme case, there would have been a table scan of the signature register every time a map is generated, unless you're storing the cumulative counts for each constituency elsewhere. And in any case, you were generating a map graphic, and I conjecture that this was done server side and then sent to the user. So what did they do about it? A decision was made that the system would only generate a map every 30 minutes instead of on demand, and that users could only cause the map to be displayed, not generated. And that reduces the resource contention between signature collection and map generation. You can imagine that there would have been quite a lot of contention for the signature register, because when you have a very rapid signature rate, that is, those constitute writes on the signature register, while the map generation is doing reads. So you have contention for these things going on continuously, and those who are signing are not going to be locked out while the map is being generated. So you can imagine that there would have been divisibility problems, locking coordination problems, synchronization problems galore, all of which would combine to degrade performance significantly. Well, how might they have prevented this in the design phase and in performance testing? In the design phase, you want to identify points of contention for read and write data between the use cases, and identify points for hardware resource contention as well. And then I would advocate building a coarse mathematical model that allows prediction of resource saturation based on extreme mixes of demands for different use cases. Then one would establish rules for how frequently write threads can be blocked when the map use case is running, or how frequently the map use case can be invoked and by whom. And that in the end is what they did. They said this use case cannot be invoked by the general public. We're going to build the map every 30 minutes and make it available, and that's that. And you need to set expectations, therefore, for how often the map should be and will be refreshed. That's going to be based on political and technical considerations, and then you set the map generation policies accordingly. Now, in performance testing, what you want to do is run tests with workloads of extreme use case mixes to assess resistance to unanticipated use case mixes. Of course, you have to anticipate what the extremes might be, you can imagine there's a corollary to Murphy's Law there, which says that whatever can go wrong will go wrong. And of course, Brexit was a very contentious issue, as we all know. Let's turn now to the New Jersey Unemployment Benefits website. The use case is that you claim your benefits after becoming unemployed, initially and then weekly. And you're required to sign up weekly in order to continue receiving benefits and attest that you haven't worked and that you applied for at least 3 jobs a week and that kind of thing, although they waived that during the pandemic because it wasn't realistic, especially for people with pre-existing health conditions and so on. And the system had flagging mechanisms to see whether the claims needed to be audited and adjudicated. And that meant that a staff member from the New Jersey Department of Labor had to log in. Now, admittedly, there was a backlog. You can't just ramp up your staffing. In a cloud-based system, you might be able to auto-scale the entry of claims at least, and therefore keep up with the demand that way. The problem here is that people kept on retrying because they were being kicked off, and that placed a huge load. There was another problem, which we'll see in a moment, and that is that the website was inherently unscalable. The black swan that we had there was a sudden increase in demand for benefits as large numbers of residents were laid off because of the COVID-19 pandemic. And that is something that was not foreseen when the system was built, but the system wasn't architected to respond to a surge like that either. So the consequences were an unusable website with very long response times, or no response at all, or no accessibility at all, benefits being delayed for many months, which is a nasty social cost. And even if people had data stored in the website, it was being corrupted or ignored, including banking information, which necessitated corrections by staff. And I know of one case in which the banking information was ignored and a debit card was created to hold the funds for hold the benefits for the user, and the user was never told. A side benefit of this, of course, is extremely overworked staff who have to correct the problem once they eventually get around to calling you, and unreachable help desks, which are overloaded because of the extremely overworked staff. So, what are the published characteristics of this website? The business logic was written in COBOL, and from what I could see, there was no means of replicating the instances of the business logic unless they resorted to containers or something like that. The claimants and the state agents access the system interactively. The verification and payments in the system are made in batch mode overnight, which is fair enough because you're going to make deposits in claimants' bank accounts and so on. And the debit cards are replenished or created for those without accounts. I don't know the characteristics of the backend database, so I don't know whether replicating the business logic would have been effective because I don't know whether the backend database would have been overloaded as a result. But I hope they made a modeling study to assess that so that they could decide whether the backend database, which is probably more modern than the COBOL business logic, would be able to cope instead. Well, how did they resolve this? Initially, they told users to return later, even if they had succeeded in logging in. Eventually, and this is the pattern that's still in use today, they allowed users to sign on only at scheduled times based on the last 4 digits of their tax identification numbers. The aim there is to limit peak loads by requiring people to log in even at 8 o'clock on a Sunday morning in order to make their claims. And for a given last 4 digits of a social security number, you have a choice of about 4 different times during the week when you can make your claim or create a claim or whatever. Okay, some historical and technical notes here. And these are largely social and political, but technical as well. There was a report issued in 2004 which said that the New Jersey state IT systems for benefits taxation and regulation were not perceived as vital infrastructure by the politicians or by the public. They were underfunded and at very high risk of overload, even under conditions that are far less stringent or severe than what we've experienced in this country in the last year. Until the pandemic, IT issues were not as visible to the public as potholes, collapsing bridges, crumbling school buildings, and the like. And the systems were never upgraded to make them robust in the face of increased traffic in the case of failures or partial outages. You have the additional problem: the technology use is not well supported. You can't find knowledgeable, experienced COBOL programmers in large numbers these days in order to do upgrades under emergency conditions. So you have a considerable vulnerability to overload and obsolescence and an inability to scale. And that was known publicly for nearly 20 years and nothing was done about it. So what general recommendations could be made under these circumstances? And I would note that these apply to any public sector system and to any private sector system that is accessed by the public. You need processes for preventing IT obsolescence and for ensuring robustness in the case of spikes. And we know how to do that. We know how to migrate technologies to the cloud. We know how to create containers. We know how to do assessments every so often to ensure that the systems can be supported, that they can continue to be scalable, which is what the private sector does or should be doing anyway. And you want to also recommend, we also want to recommend assessing the performance impact of changing mixes of use cases and changing demand patterns using mathematical models and testing. You use the mathematical models to help you to design the performance test cases to see whether the system is going to crash or not. The problem with a mathematical model is that you may not be able to capture everything. The conventional models really focus on hardware resource usage, but these days we have to focus on software bottlenecks like locks and discrete resource pools and things of that nature as well. Any one of those has the potential to become a software bottleneck. We also need to think about network capacity, user footprints and things like that as the number of users it increases dramatically. So these two examples have some similarities, but they're also quite different from one another. In the case of the UK, you had an unexpected mix of use case demands caused by dramatic performance degradation and crashes. As far as I can tell from press reports, the system was otherwise fairly up to date. Eliminating on-demand access for map use case reduced the overload problem. And the maps were then produced according to a supposedly politically acceptable schedule. And no change in technology was needed in the short to medium term in order to support that. I suggest that prospective analyses might have prevented the problem. And these need not have been done when the system was built. The fact that they were able to fix the problem so quickly suggests that they should have anticipated that this use case black swan would emerge, and they should have done something about it when the possibility of a parliamentary grievance petition regarding Brexit arose. In New Jersey, on the other hand, you have a legacy system with obsolete technology that's hard to scale and maintain, not least because the staffing isn't there. They attempted to mitigate overload by forcibly spreading the peak load over an entire week. The system is not architected for scalability in case of sudden load increase. The load spreading is over time is a mitigation. It causes inconvenience, but I guess the theory is if you're unemployed, you can log in on a Sunday morning or early on a Monday morning or whatever anyway, in order to make your claim. But overall in the state, major technical modernizations are needed, if only to speed up the processing of claims anyway, because you want to be getting your benefits within a week if you're hard up. So there was a social cost to this neglect. Regular technical assessments are needed to support current performance expectations in the face of a sudden increase in demand. Well, that's a polite way of saying, well, everybody's using the web these days, so they expect fast response time, even from the public sector when they log in, when they go online. Of course, that hasn't always happened. We know about healthcare.gov having a disastrous rollout because of lack of performance testing and so on. And also in the case of New Jersey, the need for scalability and robustness was never identified, or identified a long time ago, and it wasn't addressed recently. So one of our issues is that success at preventing performance, scalability, and similar problems is not noticed by or visible to the user base. The poor visibility of success underscores its value rather than diminishing it. Hey, nothing happened in spite of all the load. That was wonderful. What if analyses and attentiveness to function under potential overload do not receive sufficient priority, either in the private sector, probably, certainly not in the public sector? If you do what-if analyses of extreme cases, that enables the assessment of robustness in the face of sudden changes in demand patterns and identification of areas for improvement. Another change that needs to be made is the IT system. You need a mindset that IC systems are part of infrastructure, just like roads and bridges, and should be maintained as and tested as such. My focus here has been on websites facing the public, but the issues and techniques are also relevant to other kinds of monitoring and control systems and to systems in the private sector. Many of the black swan issues are foreseeable, but not always foreseen or of concern to influential stakeholders. That's a political and social problem which we need to mitigate by technical means. These are managerial, since the technical expertise is there, the challenges that we as software performance engineers faced are managerial, social, or political rather than technical. So we need to persuade the systems owners that engineering for black swans enables reliability, performance, robustness, etc. And it might even enable cost reductions in the long term. And education about performance and capacity planning in conjunction with other training is key. Yesterday in the WEPI workshop, we were talking about the possibility of embedding performance training in other courses so as to spread the word and make it more acceptable. You make it part of the routine rather than having it be perceived as a discipline or a subject in its own right, even though it certainly can be. The other thing is that you need continuous assessment and consistent assessment of system evolvability and technological currency in order to assure scalability. After all, we're having auto-scaling and things like that because of fluctuating demand, because we need to make good use of resources. And existing systems should be treated that way as well. And we know how to do this. The methodology is there, and we should apply it to guarding against many black swans. Thank you very much.